However, I hope you don't mind if I give this lecture in English. So behind me, these bright glowing dots, this system is currently the backbone of a new type of computer that will be able to solve problems that will always be impossible using conventional machinery. So what makes this so? Well, these dots are actually individual atoms. There's exactly 25 of them, you can count them. They're glowing because we're shining laser light on them. It's a very exotic piece of matter. These atoms are incredibly well isolated from their environment. They're in a vacuum chamber. They're suspended in free space with electrodes that you can't see. There's no air to collide with them. They're not part of a material or a solid. They're not even on a surface. They're by themselves. These atoms are lonely. And as I'll tell you, this is where the opportunity lies in building a new type of computer that's based on the sheer isolation of systems like this. And it comes from the fact that the laws of physics are different when you're nearly perfectly isolated from the environment and you're a very simple system like an atom. The laws of physics are called quantum mechanics. Quantum mechanics. So I see I do have enough time to give you a little seminar on what quantum mechanics is, because it is not hard. Whenever I hear quantum mechanics is hard, I don't like to hear that, because it's not hard. It's just confusing. It's beyond our everyday experience. We have very little intuition on the fundamental concepts of quantum, but it's not hard. The rules are very easy to state, and they're very easy to apply, and I'm going to tell you these rules. There's exactly two, and only two rules, and I can do it in about 2 or 3 minutes. You may have heard that things that are quantum mechanical behave like a wave. Everything's a wave. You may have heard this. That sounds abstract, and that's only one rule. Rule number one: quantum mechanical things are waves. Well, we experience waves in everyday life. Water waves on the surface of a pond, sound waves, and many phenomena that occur with wave-like dynamics. We're used to these things. One in particular that's very important for these quantum computers, I'll get to that in a moment. Waves are all over the place. They're not in one location. So when you throw a rock into a pond, the wave emanates from the center, and it's everywhere. Where is the wave? Well, it's everywhere. Well, quantum waves are like that. Quantum waves allow superposition. They allow things to be delocalized. So this glass of water, for instance, if it were a quantum object, it's not. There's air pounding into it. I'm looking at it and so forth. But if this were a quantum object, this glass of water could be in two places at the same time, because it's a wave. It has a crest here, and it has a crest here. And the way that wave oscillates is governed by mathematics that's no more complex than the mathematics behind water waves. So we're very used to rule number one. Everything's a wave, and it waves, it undulates according to a particular equation. Okay, I said there were two rules. There better be two rules, because we never experience things that are in multiple places at the same time. We never see that in everyday life. So we have to invent rule number two. And here's the problem. You know, in physics, we like to say that we're the king of science. We can put one rule at the very top, and everything is derived from that rule. We're at the top of the pyramid. Well, not so with quantum physics, unfortunately. And this is probably why Einstein didn't like the theory, and many others don't either. There's two rules, and they have nothing to do with each other. You can't derive one from the other. And that's why quantum physics is controversial, let's say. It's strange. Well, what's rule number two? I've been putting off the punchline. Well, tongue-in-cheek, rule number two says that, remember rule number one, that you can have things in two places? Rule number two says, rule number one only works when you're not looking. That's basically quantum mechanics. Now, well, what happens when you do look? We have to make an observation. Well, this is where things really get bit crazy. Quantum mechanics says that when we do observe something like this glass being in two places at the same time, it randomly pops into one of those two positions. And then the world makes sense again because we only see glasses in one place. But as long as we're not looking, in particular, this glass could be in two places. Very strange. Now, I think it's strange on two accounts. One of them is that when you do look, you can't predict where it's going to end up. It's like tossing a coin. There's probability involved. We have to use probability in quantum physics. And it's the only theory in all of nature where we have to use probabilities. You all know what probabilities are. I do have a coin in my pocket. We use probabilities to express our ignorance. So when I toss this coin, we say it's a probability of 1/2 that it's a heads or a tail. It's only because we're ignorant of exactly how hard I toss the coin, exactly the pull of gravity and so forth. We know weather prediction is probabilistic. It's going to rain with a 50% chance. That's because we're ignorant about the inner workings of what goes on in the upper atmosphere and so forth. So probability, we're familiar with it in everyday life, but it expresses our ignorance. In quantum mechanics, probability has to be there. It has to be there. It's not about ignorance, it's about it has to be there, and that's why it's strange. Einstein has so many wonderful quotations. One of them has to do with probabilities. He said, God does not play dice. In other words, this cannot be the fundamental theory of nature. Well, unfortunately, Einstein was wrong. Apparently it is. It's been tested to higher precision than any other theory in all of nature. It's here to stay. So that's quantum physics. 2 rules. That's it. Now, there's math behind that wave. That wave, I think I said that earlier, we can control the way the wave interferes, right? We can throw rocks in the pond and we can alter the wave. That's the external control, but still, that's just mathematics. The concepts are confusing, but they're not hard. The other thing that's strange about rule number 2 in my book is that it seems that by looking at something, you affect that something. I mean, how could it be that this glass changes just because I open my eyes? So there's some confusion there as well, and I think a lot of people tend to take this subject and go into philosophy. What does it mean to be real? I mean, I'm talking about the existence of this glass. Does it exist here, or does it exist here? Quantum says it's an and. It exists in both, and then when I look, it pops into one. So in physics, we don't like to define consciousness, what it means to observe something, but we can do this without invoking the action of the human brain or any conscious being. Well, if the glass is over here, and not over here, then the air in the room has made a decision. The air is over here, and the air is not where this water is, right? It evacuated. But if the glass is over here, the air had to decide to do the opposite. Okay, let's get rid of the air. We'll pump out the room, no air in the room. It's a nearly perfect vacuum. Nothing's nearly perfect. Let's say there's 1 molecule of nitrogen in the room, and this nitrogen is going like my finger here. Well, if the glass is over here, the nitrogen's going to go straight through. But if the glass is here, the nitrogen's going to bounce off. So that single molecule has to make a decision. What does it do? Well, in physics, we bring it in. If we went through all the trouble of putting this glass in 2 places, we can add a single molecule going in 2 directions. So the molecule hits that wall, and it hits that wall. Well, now what does the wall do? This wall is going to feel the recoil, or that wall. Both of them do. Well, the whole building shakes one way. The whole earth gets involved. And so what we do in physics is we cut the system off. We say we have isolation. That's rule number 1. And an observation simply means we have interaction with the environment. We've opened it up. And so this picture here of these atoms, by the way, why do you see them? We're shining light on them. When we turn that light off, the atoms are still there, but they're nearly perfectly isolated. It's a great test bed to do quantum. All right, so what does this have to do with computing? Well, in fact, we can use superpositions to store information. And there's a wonderful analogy between this superposition idea and bits in nature, 0s and 1s. And it involves an optical illusion. So here I've drawn, you've done this before, you draw a cube on a 2-dimensional surface with ambiguous perspective. So is that front face down and to the left, or is it up and to the right? Well, it's sort of both. And in fact, it's a little like a superposition, and typically, your mind locks onto one perspective and it stays that way. That's like a measurement. It pops into one or the other. If you close your eyes and do it again, you may find the other state. So this is sort of like representing data of both 0 and 1 at the same time. Okay? That's only an analogy. There's nothing quantum about this. But the beautiful thing about this analogy is that it scales to more bits. These are called quantum bits, by the way, qubits. They can be both 0 and 1 at the same time. Well, when we put two of them together, there's a word for this. We call it entanglement. Now, if you study these two cubes, you'll notice that their perspective typically locks in the same direction. If you close your eyes and do it again, you might find a different perspective, but they're usually the same. This is what quantum entanglement is. Einstein, quoting him once again, he called this spooky action at a distance because there's no physical wiring between them. It just happens that way. So this is an analogy, but in quantum mechanics, this is real, the idea of having entangled connections. It's wiring, I like to say it's wires without wires. And this is why a collection of atoms like I showed, there's no wires between them. We can prepare them in entangled states to do computations. So what happens when we put more and more qubits together? And this is the really good part. With one qubit, there are two levels, 0 and 1. With two qubits, there are four possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. Every time you add a qubit, you've doubled the possibilities. Okay, with 3 qubits, 4 qubits, that's 16, not so impressive. But with 300 qubits, which is not that many atoms, there are more possibilities than there are atoms in the entire universe. So a quantum computer with 300 qubits, in a sense, has more capacity than if every atom in the universe were part of a regular computer. So it allows us to think about problems in a new way. What are these problems? Well, they're not everyday. I'll cut to the chase. We don't know exactly the killer application of quantum computers. It's probably going to lie in something like optimization. I show this picture of a landscape. What's the highest peak in that mountain range? Well, it's easy to see it, that one in the front there, because it's only two-dimensional. There's a latitude and a longitude, but the highest peak depends on all of that information of the entire landscape. What if I give you a function, not of 2 dimensions, latitude and longitude, but it has 1,000 dimensions, 1,000 inputs? What's the optimum value of that very complex function? We don't know. We can't draw it for sure. These are really hard problems, optimization problems, and they have a huge application space in all of science, technology, and life. That molecule on the left is caffeine. It has over 100 electrons. Those electrons optimize their arrangement. We can't calculate the structure of caffeine because there's too many configurations. The other molecule it's a nitrogenase that breaks up nitrogen into ammonia. We know bacteria uses this type of nitrogenase to form fertilizer. We don't understand why and how it works. And it turns out, I was surprised to hear that about 3% of the world's energy production goes into a very high temperature process for forming fertilizer. And we know that this nitrogenase does it almost for free. Understanding that molecule is beyond our capability now. If we're going to understand it, it's going to involve a quantum computer. You may have heard of the traveling salesman problem. It's a logistics problem. What's the shortest path between all these cities? With only 100 cities, there are more configurations than there are atoms in the universe, so you can't solve these problems. Of course, economists and so forth are very interested in problems like this. So back to the hardware. Quantum computers are said to be more different than our current computers than those current computers are from an abacus. And the reason is, an abacus and a laptop are the same, they follow the same laws of computing, even though one is a lot faster than the other. So there are exotic hardwares to build these quantum computers. The one I work with most is based on individual atoms, and these atoms are levitated above a chip. You can see that chip and the system behind it. It's very complicated, and I have a startup company, IonQ, in College Park, Maryland, that's building these. We're competing with Google and IBM and so forth. Honestly, we have better hardware than them. But to me, the most exciting feature of this field is that quantum mechanics is no longer for physicists only. It's for computer scientists, economists, sociologists, anybody that wants to solve complex problems. Thank you.